All right. Check spelling. Okay. All right. Happy ILW to everyone. Right now it is 7:30. I finally got out of bed because my core hurts more than I thought it should. Anyway, okay. So for today, we'll be answering select problems from problem set 4, namely problems 5, 8, 10, and then just as a little extra treat, maliito, as a little extra treat, number 11. So let's begin immediately. Number 5. Your bathroom faucet is a bit leaky. Scared of messing your pipes up, you call your plumber. They say a plumbing job costs 1,500 pesos and they guarantee that their work will last for a year. Suppose that you know your faucet leaks 1 drop a second, with 12,000 drops making up a liter, and that according to your water utility company, a cubic meter of water costs 28 pesos. I asked my parents for this. Costs 28 pesos. Would it be more economical to leave the faucet leaking all year? Right? So, let's begin our highlighting process, right? All right. Your plumber says a plumbing job costs 1,500 pesos. That's a number. Let's turn that blue. And they guarantee that the work will last for a year. Their work will last for a year. That means our comparison should be in terms of what is happening. My mouse is acting up. Okay, supposing they guarantee their work will last for a year. There you go. Suppose that you know your faucet leaks 1 drop a second. So that is another number. With 12,000 drops making up a liter, another number. And that you know, according to your water utility company, a cubic meter of water costs 28 pesos. Would it be more economical to just leave the faucet leaking all year? They are trying to say, or they are asking us a yes or no question. Would it be more economical? Should we leave the faucet leaking? Will that cost us more water than just having it done by the plumber? Okay. So this is quite a simple question. It's just one case, right? You just have to say yes, it should be more economical, or no, it will not be more economical to leave the faucet leaking. All right. So let's just say our given. Let's say our given are our options. So case A, we just get the plumber to do it, right? Case A, we give out or we hand out 1,500 pesos for the plumber per year, right? This is our plumbing job, right? Plumbing job. And then for case B, if we do leave it leaky, right? We know that it will cost us 28 pesos per cubic meter of water, right? And so now to keep it fair, to keep things fair, right? Let's start our solution. To keep things fair, because you guys will learn about this when you enter your economics. I don't know if there should be an engineering economics for MEM students. I'm not sure where that is or what the course code for that is. But to keep things fair economically, of course, you're going to have to compare different cases on the same time scale, right? The time scale will be set at a year, right? The time scale will be per year, right? And plus also we haven't specified here the volume flow rate of your leaky faucet is 1 drop per second, right? 1 drop per second. So just so we know, right, the definition of your volume flow rate is just really the time rate of change of your volume, right? With respect to time, that means, right? Or if you want things to be a bit more macro, if you just don't want to deal with the calculus of very small things happening in very small time scales, just think about a change in volume over a change in time, right? And that means, right? That means that your change in volume, aka your volume, is just your volume flow rate, right? Your volume flow rate times your change in time. This will be, of course, this will be a year, 1 year, right? That will be 1 year. And so let's begin, right? This is just going to be one long, what do you call this? One long conversion factor, like multiplication exercise, right? We know that our volume flow rate is 1 drop per second. And we know also that the problem states that you need 12,000 drops for you to get 1 liter of water. And then 1,000 liters of water would finally get you to a cubic meter of water. Right? Why did I go to cubic meter? Number one, that is the SI unit for volume. And also, number two is that the water utility company specifies your cost per cubic meter of water. So everything is very convenient, right? And so once we cancel everything, cancel, you'll be left with a meter cubed per second, right? Which is indeed, right, your volume flow rate. Now, for the second one, how do we get to multiply a year? Well, that's just a year. And then, and then what? In a year, there's supposed to be 365 days. And each day, you're going to have 24 hours. That's not up for debate, right? If you want to be very pedantic, this is like 365 and 1/4 because of a leap year or something, blah, blah, blah. Doesn't matter, right? As you will see. And then each hour, you will have how many seconds, right? You will have, for an hour, you will have 60 minutes. Each minute will have 60 seconds. So this is quite common already as someone's being chased. Or someone's in an ambulance. That is an entourage. I hope you guys are hearing that. Just so you know what is happening. But anyway, this is quite common as a conversion factor already. You don't have to go through 60 times 60. An hour gives you 3,600 seconds. And so again, cancel tayo. Cancel. And you see, seconds on top, seconds at the bottom. Cancel. We will have cubic meters, right? And as a result, we can just put all of this together. We will have what's on the numerator. Numerators are 365, 24, and 3,600. And on the numerators, we will have 12,000 and then 1,000. This will get us our value of 365 times 24 times 3,600 divided by 12,000 times 1,000. That gives us 2.628. 2.628 cubic meters of water. And as a result, your final cost will just be 2.628 cubic meters of water. That's how much water we're wasting. And then each cubic meter of water is going to be 28 pesos. Per cubic meter, we see cancel. And now we will see, once we multiply everything here by 28 pesos, we will get the final answer, 73.58. 73.58. Therefore, if we leave the faucet running, it will be more economical to keep it leaky, right? Which is very weird, considering, of course, well, that's not what you want to do. You want to solve the problem. Apparently, the cost of the water that you're wasting is not enough to offset the 1,500 pesos. However, I mean, that's not the only reason why you're doing this kind of thing. If anything, that leak will just make you want to clean up every single day, right? Those drops of water will accumulate, and then I don't know, that kind of thing. Plus, when things are leaky, of course, like when you open the faucet, it'll be more uncontrollable, something, blah, blah, blah. It's not a great kind of thing. So if anything, this 1,500 is to like give you peace of mind, so you don't have to go crazy cleaning every single day the sink, right? I'm saying because I kind of know a similar experience, right? Thus, it would be more economical to economic cat to leave the faucet leaky, right? This would be our answer, right? And this is less of a conservation of mass kind of thing, more just like a sanity check, a salience check for us, just to know, okay, we know our volume flow rates, we know our conversion factors, shall we say. Okay, so again, if you guys have questions about these questions, then of course let me know, right? But since there will be no questions as I'm recording this, unless someone is asking because someone is stream sniping, I'm not even streaming. Anyway, let's now go to number 8, right? Let's now go to number 8. 10 kilograms of a gas in a piston cylinder assembly is compressed from atmospheric pressure and at a temperature of 24 degrees Celsius to a final pressure that is 7 times the initial. Provide the amount of non-flow work in kilojoules needed to perform this process, following the details below, given that the ideal gas model applies for these gases. So there are 3 letters here, right? So we will have helium gas is used for an isometric compression, ammonia is used for an isothermal compression, and air is polytropically compressed such that its final temperature is 165.38 degrees Celsius. Okay, so let's go ahead, let's highlight now, just so we know we have a first go at everything, and then we start highlighting. 10 kilograms, of course, of a gas in a piston cylinder assembly is compressed, okay, of a gas. So we don't know yet. Interesting. We don't know yet what the what do you call this, what the substances are. They will be specified in the given letters, right? In a piston cylinder assembly, this means that we will be working with a closed system, is compressed. This is the operative word, compressed. If ever we're going to have any kind of answer, it should be negative, as you can see, right? From atmospheric pressure, this will be our initial pressure. So I'll call that blue. And at a temperature of 24 degrees Celsius, again, that is blue, that's the number, to a final pressure that is 7 times the initial, okay? Provide the amount of non-flow work. That is what we need. So that would be red. Needed to perform the process following the details below, given that the ideal gas model applies for these gases. So that will be another detail. Helium gas, right? Ammonia. Ammonia. Right? And then air. So isometric compression is what we are looking for. Isothermal compression is again what we're looking for. And air is polytropically compressed such that its final temperature is this thing, right? So we will have everything we need, hopefully, right? This kind of looks like yung lyric breakdown in Genius. Anyway, I'm being a bit more casual because it's Independent Learning Week. Okay, now let's start with letter A. Helium gas is used for an isometric compression, and the thing about this is that there really doesn't need to be a lot of solution for letter A. Yeah, for letter A, right? This is given. We know that the mass of everything here specified will be 10 kilograms. We know also that state 1 is going to be given. It is atmospheric pressure. So P1 is going to be 101.325 kPa absolute, right? Whenever we're dealing with ideal gases, we always need to turn everything into their absolute components. 24 degrees Celsius, you're going to have to turn that into Kelvin. So 24 plus 273.15. That will be 297 point, whoa, 297.15. 297.15 Kelvin, and then everything else follows. The ideal gas model applies. The ideal gas model applies. Now, letter A, right? Your substance is helium, right? And it's an isometric compression. But because this is especially the case, isometric, agad ang lumabas, we already have our answer, right? Whenever we are dealing with a closed system, right? Closed system, we know that work only depends on if the volume of the closed system changes. If the closed system expands, that means the gas inside has done work, right? That means the gas inside has done work. And if the system closes or contracts, that means that some outside force, some external force has acted upon the system. Someone else has done work on the system. Right? This is again connecting different concepts from topic 3, and again the entourage. There are fewer vehicles now. Okay, anyway, because this is isometric, we know that the volume does not increase nor does it decrease. It's just going to be the same. And if that is the case, we know already that there will be no work because it's isometric. Right? Because it's isometric. Since V is equal to constant, right? Or you can also say N is approaching infinity. You can use multiple equations for this, but the most convenient would be to say immediately that it is 0, right? You can also say, you know, your work non-flow is going to be, I don't know, P2 V2 minus P1 V1 all over 1 minus n. The thing about n is that it's going to go to infinity. So 1 minus infinity is negative infinity. Yes, sure, it's negative, but it's a really big number. It doesn't matter what you put up in here, unless that's not infinity. That will still be 0, right? That will still approach 0. Or if you would want, well, you can really just put everything in here, right? But that still will not change a thing. It will still go to 0, right? Now, letter B. Our given this time around is what? Ammonia? Ammonia. Ammonia is used for an, ammonia is used for an isothermal compression. And the thing about this is that, isothermal, if you guys remember from the last video that I've created, one of the last videos I've created, or basta, one of the techniques that I've shown you guys, because there are lots of ways you can try to go about the first law of thermo in reviewing, in studying that kind of thing. If you don't particularly care about how it's derived, how the formulas are derived, you can just use 2 out of the 5, right? There's supposed to be 5, right? But you can just use 2, as in the one wherein, right? As in the one wherein this is your work non-flow, P2 V2 minus P1 V1 all over 1 minus n. This works for n is not equal to 1, aka that's not isothermal. And the other bit that you should know if ever it is isothermal is PV ln V2 over V1. Why did I not specify what number this is? It's because this can be P1 V1 or this can be P2 V2, right? This is for n is equal to 1. Now what, right? Technically, we do have the values already for P1 and, there's actually no value for V1, right? So how are we going to do something like this, right? Because we know that the ideal gas model applies, there's another way for us to understand, oh, by the way, this is n equals 1. So we will have to use the second equation. There's another way for us to understand this equation, this PV ln V2 over V1, right? Excuse me. And the way for us to understand this is, well, what is PV equal to in the ideal gas law? That will be equal to MRT ln V2 over V1. And again, I'm not putting 1 or 2 in here because, well, it's isothermal. T1 is equal to T2, right? And so now let's do a little check. We know this. We can compute this value of R because we know it's ammonia and we know the temperature. The problem is we don't know the values of V2 over V1, but there is a fix, right? There is a fix. Because we know that this is an isothermal process, what else can we pull out of our bags, our formula bags? If you said Boyle's law, congratulations, yes, that is correct. But also, if you're lazy like me, you can just say, you know what, just apply a combined gas law to everything. To which I say, yes, you can do something like that, right? So P1V1 over T1 is equal to P2V2 over T2, right? This is our combined gas law. And the thing about this is now, this is isothermal. Therefore, you can just cancel both T1 and T2. Right? As a result, you will arrive at Boyle's law. P1V1 equals P2V2. Now, here is my point. You can make V2 over V1 from here. If you can see this, you can bring down V1 and bring down P2. As a result, what will happen? You will get V2 over V1. I'm reflecting the as I go. I'm sorry. I'm reflecting the equation as I go. V2 over V1 is equal to P1 over P2. So in actuality, you can also re-evaluate this as MRT ln P1 over P2. The magic about this is that this does not only work when it comes to ideal gases, it works period. Right? For fluids, this works as well, right? As long as, you rewrite this as PV, right? Because that's not always the case when we're dealing with fluids. This is only the case when you're dealing with ideal gases. But this re-evaluation, it works, right? Why? Because look at this. And then I will say, I can generalize from here that, wait a second, that's just saying the same thing as PV is constant. What does this mean again? PV is constant. Wait lang. This is PV raised to 1. If N is equal to 1, this is isothermal. So, this manipulation works no matter what, as long as it's a fluid, of course, right? And so, if we look back, we have this, we can find this, we know this, and this. And now we can solve, right? Now, work non-flow will be as follows, 10 kilos, 10 kilograms. And now, what is the R of our ammonia? Well, that's just going to be R bar over MW, 8.3143. It's true, I love you, right? 83143. And then this will be kilojoule per kilomole Kelvin. And then, what is the molecular weight of ammonia? That will be 17, right? So for NH3, NH3. For N, you have a molecular weight or molar mass of 14. For each hydrogen, you will have 1. There are 3 hydrogens, so plus 1 times 3. That will give you 17. So 17 will be my answer here. Although, if you don't know this, of course, there's always another way, which will be through the tables. Right, let's look at the tables. Ammonia here. Whoa! If we can zoom in, not that much, of course. Ammonia has a molecular weight of 17.03. So 17 is good enough for me at the very least, right? Cancel, 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 cancel. And then we will have, what is T again? Our T is 297.15. 297.15 Kelvin. And then we can cancel as well. And then ln. And then ln. ln of what? P1 over P2. The thing about this is that I don't want to compute P2 because I'm very lazy. All I know is that your P2, your final pressure, is going to be 7 times your initial, P1. So it actually doesn't matter that the pressure of this mass is atmospheric pressure, right? It doesn't matter. As long as your final pressure is going to be 7 times your initial, that will not matter. So we can now cancel. So all in all, we are just looking at numbers now, and then our final standing unit will be kilojoules. 10 times 8.3143 all over 17 times 297.15 times ln of 1 over 7. This will be in kilojoules. So let's try to do this now. Negative 10 times 8.3143 times 297.15. Oh, times 297.15 times ln of 7 divided by, what is this again? 17. Our answer will be negative 2827.97. Negative 2827.97 kilojoules. This is your work non-flow. There you go. There you go. Right? Okay, zoom out tayo. And also, what did I just do for this for this one, right? Clearly, this is not the same as this, but it is, right? I will invoke a law of exponent or a law of logarithm. If you see here, ln of 1 over a, you can just write that down as ln of a raised to negative 1. And again, the superpower of the logarithm is to break that down, put the negative 1 down into the coefficient side. So you will just have negative ln of a. So these two things are the same if you still haven't connected those two facts yet, right? So now, negative 2827.97, that is our answer, okay? And now for letter C, air naman will be our our working substance. So okay, let's go with air this time around. Air, and then polytropically compressed such that its final temperature is 165.38. 165.38 degrees Celsius. Of course, we are dealing with ideal gases here, so we need to turn everything into Kelvin. 273.15. 438.53. 438.53. And so now you might be saying, wait a second, this sounds incomplete, right? I don't even know the letter N, right? I don't even know the letter N. Well, at least, oh, sorry. Oh, I didn't put it here, right? Where is that? Right. To a final pressure that is 7 times the initial. Sorry, I didn't put it here. P2 is going to be 7 times P1, right? Which is, if we really wanted to do that, we can just multiply by 7, 709.275. 709.275 kilopascal absolute. Okay. The thing about this is now this is complete, but sadly, we don't know the value of letter N. And so we're going to have to find that out ourselves. Now, let's do this. And we have values of P1, P2, T1, and T2. This is only applicable when we're dealing with ideal gases, and luckily we are, or the problem says we should be dealing with ideal gases. Therefore, this can really just be summed up into one relation. What is the relation for pressure and temperature? This is what do you call this? this is succinctly summarized by Tito Pepito Kick. Tito Pepito. Nin pala, nin. Not kick. Pepito. And then nin. N minus 1 over n. Or, I would like to turn everything around. Right? So, what you can do is you can apply a negative 1. Raise everything to the negative first power. And as a result, all the numerators will go down. All the denominators will go up. This is the one I like using more. P2 over T1, P2 over P1, and then n minus 1 over n. Now, why is this more important to me? Because, well, I just like the look of it more. Because everything will be bigger than 1. In this case, what do I mean? Well, let's substitute everything. 438.53, that's your T2, divided by 297.15, that is your T1, is equal to 7 times your P1 over your P1. So as a result, well, cancel, you will just have a plain old 7. 7 raised to n minus 1 over n. What do we do now? Well, the thing that we need to find is in the exponent. So as a result, we need to bring everything down by introducing an ln, right? Therefore, you will have ln of whatever this value is, for 438.53 over 297.15 all over, is equal to n minus 1 over n times ln of 7. Right? So what we can do now is something like this. We can try to simplify this thing. And how do you simplify that thing? Well, right? What you can do is n minus 1 over n can be simplified to n over n minus 1 over n. This is just going to be equal to 1. Right? And as a result, we now have this. Actually, you can shift solve this, pero this is still not very good, because your n, the thing that you want to solve, is still in the denominator, so that's not a good look, right? And actually, what you can do if you do want to shift solve so bad, because I don't know, this kind of thing makes you uncomfortable, right? What you can do is you can just multiply both sides by n, right? What you can do is multiply both sides by n. What that will do is that will cancel this, and you will be left with something like this. I will make the n's red. N ln of 438.53 all over 297.15 is equal to n minus 1 times ln 7, and then you can separate these two. And then n ln 7 minus, right, ln 7 is gonna be equal to, oh, you can now put these two together, right? Yes, right. You can now put those two together. Oops. You can now have this n times, well, ln of 438.53 over 297.15 minus ln 7, right, is equal to negative ln 7. And now, finally, if you are distrustful of your calculator, or you are a bit traumatized because it has given you a can't solve, you can just drop this down and let your calculator do the work. Negative ln 7 over ln of 438.53 over 297.15 minus ln 7. Let's see how this goes. I'll now put in my, I will now bring out my calculator. And let's see, ln 438.53 divided by, we will have a somewhat exact number, which is 1.25 or 1.250007. So something like this. So let's just round it down to 1.25 for now. Why do we need this value? Because I am very tired and I don't want to go through all of this again, right? We just want to go through work non-flow is equal to our solved formula from before, P2V2 minus P1V1 over 1 minus N. Now, sadly, again, we don't have values of V2 and V1, but all we know is that the ideal gas model applies. This is a PV value, and this is a PV value. Therefore, what you can do is take them into MRT2, then minus MRT1, and group them together. You will have MR T2 minus T1 all over 1 minus N. As a result, we now have everything in here. We have mass. We have the R of air. You guys are hopefully should be memorizing that thing. Or did I say that I was going to supply it for you guys? I'm not sure. Right? But your tables are still there. So I suppose I will not supply it for you. The values of T2 and T1 are already given for us because we have the value of T2 from this letter. And we just solved for the value of N. And now we can just put everything together, right? 10 kilos. And then our R, the R of air is 0.2871 kilojoule per kilogram Kelvin. Cancel. And then we will have T2 minus T1. That will be, what is this again? 438.53 minus 297.15 Kelvin. And then cancel. And then we will have all over 1 minus 1.25. So once we put all of this together, we will have a value of negative 1,623 1,623.61 kilojoules, right? Kilojoules is the only unit standing, and there you go. Negative 1623.56 in my original computation. So that is it. That is how you get your work non-flow. Again, your guys' questions are very welcome, right? So now, we go on to number 10, right? Number 10. Okay. For number 10, it's just going to be somewhat of a simple problem, right? Number 10, two equations for the relations regarding the specific heats of ideal gases are shown below. If you always know the values of K and R, what will be the equations to obtain Cp and Cv? Right? If all that is given to us is the fact that Cp is equal to Cv plus R, and that your K is equal to your Cp over Cv, how do we get our formulas? How do we get our formulas for Cp and Cv? Right? Cp and Cv as a formula of K and R. How do we get there? Because already the values are here. Already the formulas are here. Right? I've explained them to you in class, and I've given actually Cv equals R key. Right? R over K minus 1. But how do we get there? Right? Well, you apply, algebraic manipulation. Right? And so let's start off with something like this. This thing is very important. This thing is very important because it holds a ratio between Cp and Cv. K is actually the ratio between Cp and Cv. And so if we multiply both sides by Cv, you will get Cp is equal to K times Cv. Now, if you apply that to your first equation, right? Let's label this our first equation. Let's label this our second. Substituting to 1, right, you will get something like this. K times CV is equal to CV plus R. As a result, what you can do is now you can, because you know the values of K and R, you can solve for CV as it is, right? So if you move your CV here, you will have K CV minus CV is equal to R. If you then, what do you call this? If you then group the common CV, you'll get CV times K minus 1 is equal to R. And that is how we get CV is equal to R over K minus 1. This is your first. Right? That is your first. Now, very simply, you can just put this back here. Right? And as a result, thus, CP is equal to K times R over K minus 1. And therefore, your CP will be KR this time over K minus 1. That is the simple way to do it. Right? Of course, I'm not giving you guys any I'm cutting you guys some slack in here. Right? If you do it any other way, as long as it gets to this and you are not breaking any rules, then be my guest, right? This is completely fine to me, right? If you do some other way, you know what? Let's bulk this solution up. Let's try and do it the other way around. Let's try and manipulate 1 first and then put it into number 2. What do we mean by this? We know that CP, right? Alternatively, we know that right? We know that CP is equal to CV plus R. And because we say that CP over CV is K, we should be able to say that K is equal to CV plus R over CV. Right? And again, we can separate these two. CV over CV plus R over CV. That means that your K is equal to 1 plus R over CV. We can put this 1 on the other side. We will have K minus 1 is equal to R over CV. We can multiply both sides by CV and then divide both sides by K minus 1. Why? Because now cancel. I will be left with CV on the left side now. On the left side, I will be left with CV, and for the right side, I will cancel, be left with, again, R over K minus 1. Right? And as a result, if we know that, right, if we know that your CP has to be this value, CV plus R. So that's going to be R over K minus 1 plus R. Right? And as a result, we can elevate this R. Right? We can just multiply everything by K minus 1. R over K minus 1 plus KR minus R over K minus 1. Oops. Over K minus 1. Notice, right? Notice what we did. Right? Notice what we did. And then we can just combine these two together. CP is equal to R plus KR minus R over K minus 1. Cancel. You will get the value, or rather the formula CP is equal to KR over K minus 1. Right? And if you're wondering why I'm asking you guys this, it's just that, you know, I just want to refresh your guys' ability on manipulating, on getting certain formulas, on being able to be confident with your algebra skills. Because again, like, I don't want you to be completely, wholly dependent on, I don't know, your calculators, right? That's not a very good, that's not a very good look. But then again, all right, we'll just go ahead, right? Right, that is how we're supposed to solve number 10. I've given you 2 ways. You can invent even more if you want to get a bit more particular, but that's it. Right? And now again, any questions? Very welcome, right? If you just let me know, I will attend to your questions very quickly, right? And now let's go to our extra, our bonus, our cherry on top, number 11, right? Now, okay, carbon dioxide gas treated as an ideal gas. Assume K equals 1.3, although in table A20, wow, Adobe Acrobat is acting very slowly. Oh boy. Okay, there you go. For carbon dioxide, usually, yes, usually is 1.3, as you can see. 250 and 300 here are a bit close to 1.3, and usually at 0 degrees Celsius, I think it's at 1.3-ish. So there you go. There is your, what do you call this? There is your value of carbon dioxide's K, right? This is K we're talking about. Oh, wrong thing. Here you go. Right. Carbon dioxide gas, treated as an ideal gas, is trapped in a piston cylinder assembly under 10 bar, 50 degrees Celsius. This is then expanded to thrice its original volume, interestingly. Supposing the expansion is isentropic, how much work and heat is required to perform this process in kilojoules per kilogram? Notice, that is weird. That, what do you call this? That unit is weird. Yes, it is. But also, it makes sense because, as you can see, or as you cannot see, there is no value of mass, right? They did not say, 5 kilograms or 10 whatever, right? They just said carbon dioxide gas is trapped in a piston cylinder assembly. And sadly, we don't know how much gas is in here because we only know the pressure and the temperature. Speaking of which, let's start, right? Let's start by, what do you call this? Let's start by highlighting everything now. Carbon dioxide gas, that is a detail. Treated as an ideal gas, that is another detail. Assume K is equal to 1.3, that is our number. Is trapped in a piston cylinder assembly, that is another detail we are talking about. Detail. Under 10 bar, 50 degrees Celsius. That is a number. This is then expanded to thrice its original volume. Thrice its original volume. That is a number, thrice. And the operative word here is expanded. Ibig sabihin, that means if ever you're going to get a value, right? If ever you're going to get a value of, what do you call this? Of work non-flow, it should be positive because it's expanded, right? Now, letter A, supposing the expansion is isentropic, that is another detail. How much work and heat is required to perform this process? That is what we are being asked to do. Now, letter B, more realistic processes follow n is equal to 1.2 instead. What does n mean in here? That usually means the polytropic index. And what is being asked now is how much work and heat is required to perform this operation. How much work and heat? There you go, right? Now, I have to say, before you do this question on your own, and I hope you guys are doing this on your own before I solve, you will find that your answers will be, if you do them correctly, they will be off. And I don't know what I've done before, such that I have arrived at these answers, but clearly these answers are wrong, right? These answers are wrong. Let us try and see now what will be the correct ones, okay? Let's now start by listing our pieces of given information. Right? Our given is CO2 gas. We assume now that your K is 1.3. And our initial state is 10 bar. Oops, 10 bar. So again, we can't use this. That means we will go to 1000 kPa. There's no mention of atmospheric pressure, so this is absolute, right? Now we go T1. This is 50 degrees Celsius, which is, if you add 273, that will give us 323.15. You can choose to forego the 0.15, it's fine. And we don't know the value of V1. That is why we don't have any mass. V1 is unspecified. Right? And therefore, now these values will change. We don't know the value of T2. We don't know the value of P2. All we know that the volume, the final volume, is thrice that of the original volume. Now, for letter A, suppose that your N is equal to K. Ang tinatanong, what we'll need to get is how much heat and how much work are we getting, right? And in this case, of course, the solution is clear. You're being asked for values of heat and work. What else are you to do except to apply the first law? Q minus W is equal to, we are working with a closed system, so we will be talking in terms of internal energy U, delta U. And more importantly, right, there's no mention of speed. There's no mention of altitude. So we will be left with the more basic version of the first law, Q minus W is equal to change in internal energy. Okay? And now, have more water. Okay. That can wait. We're almost done. Right? Now, what do we know about everything so far? Well, we don't know the value of Q and W, and we actually kind of don't know the value of delta U, right? Everything in here we have no clue about, but at the very least we have formulas for two of them. The formula for work non-flow remains the same. It's going to be P2V2 minus P1V1 over 1 minus N. Problem with this is that we don't know the value of V2 and V1. So we turn to the fact that, yes, this is in terms of the ideal gas model, right? This is an ideal gas, or it's supposed to be modeled as an ideal gas. So we can pivot to the more succinct version of the formula, MRT2 minus T1 all over 1 minus N. And now here's the thing. There is no mention of mass. Right? There's no mention of mass. No mention of mass. No mention of mass. As a result, we can assume you can remove the mass, or you can just say 1 kilo would work. Right? But it's better for me to remove the M entirely to do this. Why? Because let's check the units, huh? This does not have any unit at all, right? And the polytropic index is an index, right? An index is not like some, anong tawag ito? It's not a united. It does not have a unit, right? It's supposed to be an index, a ratio, right? R is expressed in terms of kilojoule per kilogram Kelvin, and these what do you call this? These temperatures are in Kelvin, so cancel. You will get your correct unit, which is kilojoule per kilogram. So as a result, all right, let's try to see. I have a value of this. I have a value of this. I have a value of this, or rather, I can search for that, but I don't have a value for T2. At the very least, there is a way forward. So let's first start off with R. R here stands for R bar over the molecular weight of, what is this? Carbon dioxide. That will be 44. So 8.3143 over 44. That will be our value of R. Kilojoule per kilogram Kelvin. Right? And if you don't know, again, right? Again, CO2. For each carbon, you're supposed to have 12. For each oxygen, you're supposed to have 16, but you have 2 of them. So 16 times 2, 32 plus 12, that is 44. Or, in here, in the thermodynamic property tables, you can just go ahead to table A1. See, carbon dioxide is 44.01. Very close. Right? If anything, that's completely fine already. Now, we have the value of R. And the only thing that's left is T2. How do you get the value of T2? Well, you're just supposed to do, or you're supposed to remember, okay, what other values can I use? There are relationships between the properties of an ideal gas when you're undergoing a process. That is yung PV. Yes, PV raised to N is equal to PV raised to N, or Tito Pepito Nin. The problem is, well, I don't know the value of P2, but I do know the value, or at least the relationship between V2 and V1. What do I mean? Yes, we know that V1, the initial and final volumes are unspecified. They have no numbers. However, because of their explicit relationship with each other, that sounds wrong. Because of their relationship with each other, we can apply T2 V2 in 1 minus N. Or, how I like to use it more, I just flip everything, T2 over T1. Actually, yeah. Tama. T2 over T1 is equal to V2 over V1 raised to 1 minus N. If I do flip everything over, aka raise everything to a power of -1, this is what happens. And now, how do we get our value of T2? We can just raise that T1. There you go. And now we can just substitute everything. T2 is going to be, what is our value of T1? 323, right? Yeah, 323. 323.15 times, this is the point. V2, we don't know the value. V1, we don't know the value, but we know that V2, the final volume, should be thrice the original volume. And then, cancel. We will be seeing times 3 raised to 1 minus 1.3, or just 3 raised to negative 0.3. We will get a value of 232.4169. I'll be using, what do you call this? I'll be using 3 decimal places just for added quality or added precision. There you go. That's your T2. And now we can get our value of work non-flow. Work non-flow will be as follows: 8.3143 over 44. And then this will be kilojoule per kilogram Kelvin. That is our value of R. And then our T2 minus T1, 232.417 minus 323.15 Kelvin. We cancel all over 1 minus 1.3, right? Because that's our value of N. That will be equal to that will be equal to 57.15. Is that the same thing I've done? 57.15 kilojoule per kilogram. This will be our value of work non-flow. Can I see if I got that right? Yeah, I didn't. Okay. Yeah, that's wrong. I don't know why that's wrong. Did I use another value of I don't know. Sorry. And also, I've been hiding something from the very beginning. Actually, we do know the value of Q. The thing about this is that we are dealing with an isentropic expansion. Isentropic means that, well, the entropy is the same. Another word, another equivalent-ish, right? Equivalent-ish word to isentropic is adiabatic, right? Adiabatic is the more specific term, right? Isentropic is the umbrella term, right? Isentropic is more, never mind. Isentropic is the more specific term. Isentropic is the more specific term, and then adiabatic is the umbrella term. Adiabatic, or rather isentropic processes, are a more kind of specific version of an adiabatic process. This means that your S is constant, of course. And adiabatic means that your Q is 0. Right? Adiabatic means that nothing can pass through. Not through walk. Right? Dia binane. Right? Binane. Walk. Or pass through. Right? You cannot pass through. What cannot pass through? Heat cannot pass through. That means that your Q is 0 kilojoule per kilogram. Right? And there's another reason why. There's another reason why this is 0. If you do know that this is 0 immediately, congratulations. You've given yourself like 5 points in the quiz if ever this comes out in the quiz. And if you don't, there is still a way. And we will show that through part B. Right? In part B, things are no longer isentropic. AKA, there are no longer, shall we say, how do I say this? They are no longer perfect. I'm not sure perfect is the correct word, but okay. Right now for part B, instead of n is equal to k, which is 1.3, now n is equal to 1.2. Right? What is the work and the heat? Right? And so same thing still applies. Q minus W is equal to delta KE plus delta PE plus delta U. The thing about this again, no mention of speed, no mention of height or altitude. We will get to this more simplified version. Q minus W is equal to delta U. And as a result, we know already what we need to do for W. For work non-flow, again, it's going to be P2 minus P2 V2 minus P1 V1 all over 1 minus N, which we don't know the value of V2 or V1, so we can just go ahead to MRT2 minus T1 all over 1 minus N. And the thing about this is that, again, there's no mention of mass, so we can remove that completely. And what remains now is, yes, we have solved for the value of R. We have the value of T, we have the value of N, what remains is the value of T2. And just like before, I'll just take a page from this directly. Let's go here immediately. We know that in what do you call this? In ideal gases, this should hold true. Right? And as a result, we can just say 3 to 3.15 times 3 raised to, now this time, this will be negative 0.2. This will now be 259. 259.4059. So 406 Kelvin this time. Right? And as a result, we can immediately get your value of work non-flow. Right? Work non-flow will be equal to 8.3143 all over 44 kilojoule per kilogram Kelvin, but we know everything already. We know that this is supposed to go to kilojoule per kilogram, so I will not bother with that any longer. 259.406 minus 323.15. This is what I'm talking about when we're going into our problems with units in mind. Once you know it, you know it, right? It's no longer a concern for us to see, oh my gosh, do the units balance? Well, you tried it before, and well, none of the units are going to change this time around, so there's no issue in trying to repeat it, right? If you want to, go ahead. To ease your anxiety, go ahead. But you've already proved that everything in here will result in kilojoules per kilogram, so that's no big issue. Let's just do this now. 8.3143 times divided by 44. 259.406 minus 323.15 all over 1 minus 1.2. We will get 60.225 or 60.23 kilojoule per kilogram. Now, so far, it is with sadness that I will tell you we still don't know our value of W. We do know already the value of our work, yes, but we don't know our value of Q yet because, well, it's not a special kind of process like an adiabatic or an isentropic process. We need to go to your delta U. What does delta U mean here again? Delta U means M delta small letter u. And the thing about this is that, well, there's no M, so it will just be this, which is equal to CV delta T. As in, right? As in CV T2 minus T1. We have values of this, right? And the thing about CV is that we know from number 10 that CV is R key, R over K minus 1. Therefore, we can just immediately do this because we know the value of R and K, right? We can just put this in now. Our value of delta small u is going to be 8.3143 over 44. And then this will be kilojoule per kilogram Kelvin. Why am I redoing the units? Because we are dealing with K, right? But you will see it's a bit futile, or rather it's a bit unnecessary, because I will tell you after I put all of this together. Kelvin, cancel, that your adiabatic index, your K, is also it's also unitless, right? It should be unitless. It's a ratio between CP and CV. And mind you, this is where a lot of people get this wrong. They put that your K is 1.2. Why did they put that? Because there was an explicit instruction in the beginning that your N is now 1.2. But mind you, this is K we are talking about, not N, right? And so as a result, we can put this all together. We can say that this delta U is going to be equal to negative 40.1505, or 40.15 will work. And finally, now we can get to the bottom of everything. Q minus W is equal to, delta U. Q minus W is minus 60.23 is equal to negative 40.15. So we just transpose that and we will get, right? Your Q is equal to 20.08 kilojoules per kilogram. This is your answer for the final question. And now the thing about this is that is how we solve the value of Q. That should be how we solve our value of Q for this one as well. Yes, that is how you do it. It just so happens that your work non-flow and your increase in delta U is going to be the same. Why? Because, look at this. Look at this, huh? Where is this? Here. In here, your work non-flow is going to be R over 1 minus N. Okay, what about this, right? Ang mangyayari is that if your N is equal to K, N is K, okay? And then, what is this value? Right? What is R over 1 minus K? R over 1 minus K is just the negative of, right? It's just the negative of, where am I supposed to put this? R over 1 minus K is just the negative of your CP. CV. Right? The thing about this now is that, okay, this thing, if you put a delta T next to it, it's just going to be negative delta U. And look at this, Q minus delta U is equal to delta U, right? And mind you, the thing about this is that, where is this supposed to be, right? Where is this supposed to be? How am I going to get there? That is your value of, okay, yeah, that is your, okay, sorry. Delta T is equal to negative delta U. And then this is equal to your work non-flow. Yan pala, sorry, work non-flow. Right? So this is your work, and you will see that your W is negative delta U. So this is now positive delta U. It's equal to positive delta U. You will cancel, and you will see that your Q is equal to 0. Right? Recap tayo, recap. I feel like I did not explain that properly. Right? So our work non-flow here is going to be, right, MR. Right? Let's remove the M for now. R T2 minus T1 over 1 minus N. In this case, or in the case of letter A, it's isentropic. Therefore, your value of N is just K. As a result, if you remove this, and if you separate this R over 1 minus K times your delta T, this will just be equal to negative CV, right? This whole thing is negative CV times delta T. That is going to be equal to your negative delta U. And again, Q minus W is equal to delta U. And as a result, Q minus negative delta U, this will be positive delta U is equal to delta U. Cancel, and therefore your Q. That is why your Q in here, your heat, will be equal to 0. Right? If you did not know this fact, or if you've forgotten this fact from the fact that this is an isentropic / an adiabatic operation, that's fine. Because if you do decide to explore the value of delta U, you should be able to know that, oh, they're just the same. And as a result, your Q is going to be 0. No heat will pass through. In this case, however, some heat did pass through. Right? It went into the system, right? Positive. And that is how we're supposed to think about this kind of thing. Right? That is how we're supposed to think about this kind of thing. The thing about this is that if you look, right, you don't need heat to power this process, right? You don't need to input a bit more heat to be able to do this kind of work, 57.15. But notice in here, even though this is doing more work at 60.23, you are also putting in some heat, some 20.08 worth of heat. And as a result, you are pumping out less energy, right? In this case, you are removing 57.15 kilojoules per kilogram of energy in the ideal gas. Meanwhile, the total between these two, because you're going to have to give 20 to receive 60, you will have to give out 40.15 only, right? And this becomes way more important when we talk about your coverage for the final examinations, which is steady flow devices. Like, why do these things matter in the first place? Like, why does work matter? Why does heat matter, right? Hopefully, I will be able to recontextualize it for you guys down the line. But suffice to say, these are our solutions for numbers 5, 8, 10, and 12. If you guys have any questions, just let me know, right? And that will be it for our problem set 4. Thank you guys very much. I will see you for your quiz, I guess, on March 10. Thank you guys. Thank you very much.